And now for section 9.2, claims about two means. So we're going to have two independent samples, so two different groups, and the claim is going to be about their two means, mu1 and mu2. So these are going to be independent samples, so sample 1 will have its own sample size, its own mean, and its own standard deviation. Sample 2 has its own sample size, mean, and standard deviation. And again, we'll write down the claim, H1, H sub O, draw the little picture, find the critical value. Since this is about the means, the critical value is going to be table A3, the t distribution. And the test statistic is also going to be a t. If you want to use the formula, it's going to look like this. But I'll also show you how to use the calculator. So who was better at hitting home runs? Hank Aaron or Barry Bonds? So from 1986 to 2006, Bonds played for 21 seasons. From back in 1954 to 1976, Hank Aaron played for 22 seasons. We're going to test the claim that the players are equally good when it comes to hitting home runs per season. So for Bonds, I took his 21 years, how many home runs he hit each season, found the mean and standard deviation. For Hank Aaron, I took his 22 years, how many home runs each season, and here's his mean and standard deviation. So Bonds his average is a little bit better, but then again, he was less consistent than Hank Aaron. So can we prove that one player is better than the other or not? So the claim will not have a number in it. It's just going to say that average for the first person equals average for the second person. H1 is not equal, so it's two tails. And as always, H sub O just has equals. So with the degrees of freedom, for Bonds, it would be 20. For Hank Aaron, it would be 21. And the rule is you use the smaller of the two degrees of freedom. So the smaller one would be Bonds at 20. So go to this row 20 right here. And I'm going to be using 0.05 and it's two tails, so I use this middle column. And then the magical rectangle says the critical value will be 2.086. So then I draw a little bell-shaped curve. Degrees of freedom is 20 using alpha equals 0.05, or in other words, 95% level of confidence. And since it's two-tailed, we have negative 2.086 and positive 2.086. Now I don't need this table anymore. There we go, got more space. So you could do the formula. So you take subtract the two means and then do the standard deviation squared divided by 21 years for Bonds, the standard deviation squared divided by 22 years for Hank Aaron. Or you could use the calculator. So on the calculator, go to Stat, Test, and then two sample t-test. You would type in all the information from over here for the two players, and then scroll down, and it's going to say, should it be pooled? So this is left over from a way that statisticians used to do it. Are these two standard deviations close enough that they could be pooled? Well, we no longer do it that way, so just say no. Anytime it says pooled, say no. And so the test statistic turns out to be 0.959. And then that would land in the middle. And when it lands in the middle, it means we did not prove anything. So failed to reject, we are not able to prove anything here. And then what about the confidence interval? So you could use the formula and calculate the error using the critical value from A3, table A3, and then use their standard deviation, etc. Or you could use the calculator. So you'll need to go to Stat, Tests, and then the two sample t interval. Type in the data, or it's already there from the last time I used the calculator. So this is still the two baseball players. And then it says that the interval goes from a negative 4.2 to a positive 11.7. And when there's a negative on one side and a positive on the other side, that's the exact same thing as getting failed to reject. We cannot prove anything here. Next, does having a filter on a cigarette lower the amount of tar? So test the claim that non-filtered cigarettes have more tar. So with filtered cigarettes, the test was done on 21 cigarettes. The average amount of tar was 13.2 milligrams, and here's the standard deviation. For a non-filtered cigarette, they tested 18 of them, and the average amount of tar was 24.1 milligrams, and here's the standard deviation. Okay, this is important. Right here it said, test the claim that non-filtered, so that's these ones right here, have more tar than these. So is 24 more than 13? Yes. But these tests, and especially the TI calculator, is set up so that you put group number 1 first. So since this was given as group number 1, I'm going to have to change this wording, or I'm going to have to change the symbol to a less than. Because it's now saying, is 13 less than 24? So is group 1 less than group 2? Okay, that's set up right. No, you can, welcome friend. There you go, good job. He was a little bit shy, did you see that? So it's a left-tailed test, and again use table A3 and use degrees of freedom of 17. So this would have degrees of freedom of 20. This would have degrees of freedom of 17, so use the smaller one. And then the critical value is negative 1.74. So I'm going to use the calculator. So using the 2-sample t-test, I type in all the information, and when it says pooled, just put no. The test statistic turns out to be negative 11, so t equals negative 11.897. So then, if you draw an arrow, that is going to go definitely past a negative 1.74. That means reject H sub O, so we did prove something. So in fact, the claim is true. And you can either word it as non-filtered cigarettes have more tar, or you could say filtered cigarettes have less tar. Either way, we actually did prove something.